So, recall that in the previous lecture we defined dissipativity of an operator. So, first we define this for an operator in a Hilbert space, and then by introducing a semi inner product in a general Banach space, we can also define this dissipativity for an operator in a Banach space. Okay. So, before coming to the Lumer-Philips theorem, so here are some simple exercises. So, it is so you should carefully go through the hypothesis of Hilbert theorem and you see these things very clearly. Okay. So, if an operator A and minus A both generate semi groups, then A actually generates a group. Okay. So, this I write as T. Now, T is in R. Okay. So, again you can now state the hypothesis of the Hilbert theorem. So, I just a densely defined closed operator A generates a group. So, Hilbert theorem is check conditions for the semi group. So, now we can reformulate that, generates a group if and only if the resolvent estimates. So, R lambda A to the power k less than or equal to m divided by mod lambda minus omega to the power k for k equal to 1 to etc. and mod lambda bigger than omega, where m bigger than or equal to 1 and omega now non-negative are constants. So, again as we did in the previous case, so you can take m equal to 1 and omega equal to 0 and then you write down the conditions for A to generate a contraction group now. Okay. So, just write down resolvent estimates, write down estimates for A to generate a contraction semigroup. As I said earlier, so most of the semigroups we come across while studying heat wave and Schrodinger equation, they are all contraction semi group or contraction groups, and in some cases they are also unitary, that is stronger than this contraction. I will come to that. Okay. So, before stating Lumer-Philips theorem, so one more definition. Okay. An operator A in a Banach space X is m-dissipative okay, m for maximal. So, I leave it to you what is that maximal is with respect to. Okay. So, to find out that if A is dissipative and so this image of I minus A is X. Okay. So, again let me recall what this dissipativity is. So, this is real part of Ax X less than or equal to 0 for all x in D. Okay. So, this condition can be replaced by anything some lambda I minus A, you will see that for some lambda positive, that is sufficient. So, in applications you need not always look for the identity, but some convenient lambda positive. Okay. So, here is the theorem. Okay. Let me just so this is Lumer-Philips. Okay. An operator okay, a densely defined operator, a densely defined so actually there is no assumption of closeness. Densely defined operator A in X generates a contraction semi group if and only if A is m-dissipative. So, like I commented in the previous lecture, you should see the beauty of analysis in reducing the complicated hypothesis in Hill-Yoshida theorem to a very simple verifiable condition. Okay. So, here in this theorem you do not see any resolvent estimate. Okay. So, only resolvent estimate might be seen only through this range condition. Okay. Otherwise you just that dissipativity again is just an algebraic condition, and this is with respect to any semi inner product. Okay, so that you should bear in mind with respect to any semi inner product. And we already seen that we can introduce a semi inner product in any Banach space. Okay, so that is why this okay, a proof is not very difficult, so just let me indicate that. Okay. This of course again follows from the Hilbert theorem. Okay, so two parts. So suppose A generates a contraction semigroup, then we already know that this norm of lambda r lambda A is less than or equal to 1 for all lambda positive. So, in particular I can take lambda equal to 1, and that proves the image of I minus A equal to x. Okay. So, that is one part is very easy. Okay. The second part, suppose A is densely defined and A is m-dissipative. Okay. So, dissipativity may not imply closeness, but the m-dissipativity. Okay. So, as an exercise, so that implies A is closed. So, because this is an important part of the hypothesis in in Hilbert theorem, so I just leave it as an exercise. Okay. So, you use the second part of the hypothesis, that m dissipativity plus that image condition, and that will imply this exercise. So, we will do a small computation here. So, let lambda be positive. So, I want to compute this. So, this lambda norm x square, okay, then for x in dA, I want to do that. So, this is the property of the semi inner product, okay, and this I write it as less than or equal to lambda x plus real part of minus real part of Ax x. Okay. Because real part of Ax x is non-negative, so I am taking negative sign here. So, that is a positive non-negative quantity. So, I can add that. So, this becomes lambda I minus A x x. Of course, I can put real part here, no problem. Okay. So, this again property of the semi inner product, and finally, you get that lambda I minus A x into x. So, that implies, so this is one important estimate. So, let me just and this holds true for all x in dA and lambda positive. Okay. A small remark here, this condition in many textbooks is defined as accretive operator. So, A is called an accretive operator, and then for M accretive you include that image condition. Okay. So, you can actually start from this if you like, but now we have this dissipativity comes naturally in many applications, and from dissipativity we are deriving this accretive condition. Okay. So, the an operator A is called accretive if this condition. So, just as a so different textbooks may use different terminology. So, you just look at the definition and proceed. Okay. So, this dissipativity and accretivity may be used interchangeably. Okay. And since A is closed, so this immediately see that image of lambda I minus A is also closed because A is closed. Okay, so that's so, but the hypothesis say that at least in one case, that is, so that's why it is sufficient to assume for any one lambda that image is exactly equal to x. Okay. So, but we are given this image I minus A is x, and with the above estimate we see that this I minus A is invertible 1 1 onto. Okay, let me write that 1 1 onto, and the inverse also this R1A, let me write that, is less than or equal to 1. So, that means this 1 belongs to the resolvent of A. Okay. So, this all exercise what we did is to conclude that 1 belongs to rho A, but rho A is open. Rho A is open. Okay. So, as a side remark, maybe I will make it for a general okay, if T is invertible and norm of S is less than norm of T inverse whole power inverse, then so this is again simple fact you learn in operator theory. So, this S plus or minus T is also invertible, and that is how you prove that rho A is open. Okay, is invertible. Okay. So, from here if you now take any lambda, so lambda minus I A, you just write that lambda minus 1 I plus I minus A. Okay. That I know that this is invertible, we have just now proved, So, this implies if mod lambda minus 1 is less than 1, then lambda also belongs to row A, and again a simple estimate, and mod lambda. Okay. We have introduced that notation. So, that's 1 by lambda. Okay. But just look at here, this mod lambda minus 1 less than 1. So, you just take the positive lambda here. So, 1 is sitting here, and now you go up to 2, and now you repeat this process and conclude that. So, this lambda positive is in row A, and R lambda A is less than 1 by lambda. And now you appeal to Hilbert theorem. Okay, all the resolvent estimates are here. So, you say that A generates a contraction semigroup. Okay. So, you just missed one thing. Let me just recall that. Okay, this generation is fine. Suppose this dissipativity. Okay, so we have to just see that. Okay, so here where is that m-dissipativity? Okay, that's fine. But here this, okay, if Tt is the semi group, we have to show that A is dissipative. So, that is missing here. Just let me just say that dissipative. Okay, so I will just continue that little bit. Okay. So, proof of dissipativity in part 1. Okay. So, we know that A generates a contraction semigroup. A contraction semigroup. Tt. Let me write that Tt. Okay. Now, you consider to see the dissipativity, you consider this Ttx minus x x. Okay. So, you semi inner product and you take the real part, and this is again using the property of semi inner product. So, Ttx x minus norm x square. Okay, and this is less than or equal to real part of this thing is less than or equal to absolute value, and then the whole thing. So, you do that. So, Ttx norm x minus norm x square. but Tt is a contraction. So, it's all norm T's are less than or equal to 1. So, that is less than or equal to 0. So, this is true for all x in x. So, in particular, if you take x in dA, so you divide by t and you take as t tends to 0. So, divide by t positive and let t goes to 0. So, you conclude that real part of Ax x is less than or equal to 0 for all x in D. Okay. So, now we come to one important theorem. So, just let me just. So, this is called Stone's theorem. This was proved many years before this Hilbert theorem theory was discovered using the spectral theory for self-adjoint operators in a Hilbert space. Now, the setup is in Hilbert space. So, let H be a Hilbert space, because we are going to use the adjoint of the operator. So, we need a Hilbert space. Okay. An operator A generates a unitary group UT. So, let me write that T belonging to R if and only if A is skew adjoint. That is, adjoint is. Just recall that this equality means dA star, the domain of definition of A star is same as dA domain of A, and domain of minus A is domain of A. So, A star x is equal to minus Ax for all x in dA. Okay. So, since we are dealing with unbounded operators, this has to be borne in mind. Okay. So, again let me just sketch this proof. It is all hidden there. So, this unitary means, okay. So, let me just, and this is particularly useful, the Stone's theorem, for dealing with wave equations and Schrodinger equations, where we expect a unitary group to be generated. So, unitary means this u of minus t is same as u of t inverse, and this is where the unitary comes. So, this is just u star t. Okay. So, this is unitary. So, yeah, so one part, suppose the A is Q adjoint. So, let me just suppose A is Q adjoint. And now, since we are working in Hilbert space, so you can easily check that A is dissipative. Okay. So, that is just in fact a real part of this inner product A x x is 0. Okay. So, you can easily check that. And again it is the property of the shell-based operators, and now okay, this if we put B is equal to I is square root of minus 1, and that implies B is B star. Okay. So, just by multiplying by this I, you see that so for a self-adjoint operator, B, this this complex plane lambda in C such that imaginary lambda is positive is in the row B, and we have this lambda I, okay, row not row R R lambda B is less than or equal to 1 by lambda. Okay. So, now you translate that to this Q adjoint operator A. So, you see that, so lambda real, lambda non-zero, this is in row A, and R lambda A is less than or equal to mod lambda inverse for all lambda real non. And from there you just conclude that. So, in fact A and minus A, they generate contraction semi groups, and from there again using the earlier exercise you see that A generates a unitary. Okay. So, conclude, okay, few more steps, conclude that A generates a unitary group. Converse is almost trivial. So, converse, okay. So, suppose ut is a unitary group, so then that means norm of ut is 1 for all t equal to 1. So, again you apply appeal to Hilbert theorem. Little more work, but what is important to show is that A is Q adjoint, but then okay, unitary group. Okay. So, use unitary to see that the generator, just write down the definition of the generator and use this unitary property of the group to see that A is Q adjoint. Appeal to Hilbert etc. to conclude A is Q adjoint. Little work, okay, but that can be done. Okay. So, with that thing we just come to end of this more or less discussion of semi-group theory. From next class onwards, we take up abstract Cauchy problem and then go to particular equations of heat wave and Schrodinger. Thank you.